Usually this section would appear somewhere in like chapter 2 as the last section. So these are called antiderivatives. An antiderivative of a function is your original one. If you know the derivative, it's the function they gave it to you. Of course, we always make notation harder than we should. We don't give you f prime of x, we give you f of x. Right? So then a lot of times notationally we say capital F of x is the antiderivative. So what does it mean to be the antiderivative? It means when you take capital F prime, you get the function you started with. But then we also have what's called the indefinite integral, which isn't so an antiderivative is a single function. The indefinite integral is all possible antiderivatives. So it's a family of functions that represents all possible functions that have the same derivative. And what do we know about that family? Yes?
They all include the plus c.
Yeah. The only difference is you can add a constant. Why would that make sense? There's only one function whose derivative is always 0. What kind of function is that?
Constant.
Constant, because it's a horizontal line, the slope is 0. So if you take any antiderivative and you add a number to it, it's still an antiderivative. Because when you take the derivative, that constant goes away. So when we talk about the indefinite integral, it would say take any antiderivative and then do plus c. And c represents a generic constant. So every antiderivative has the exact same form. But the form means you have to add this plus c. And it's because when you go to take the derivative, that c goes away. Alright, so notationally, this is what we covered in section 4.2, where you do an integral sign with an a and b. That represents a number. And then what is that number? That number is the net sign area, bounded by the graph and the x-axis between a and b. Whereas if you don't use the integral a b, you don't put in the bounds, this represents the entire family of functions that would be all possible antiderivatives. So it's an antiderivative plus c, where c now gives you the whole family. Right? So one thing tells you a number, and another tells you not just one function, but all possible functions, the whole family of functions. And for some reason, we use almost the same notation, which seems really weird. And it's because we leave you in suspense until you do the prep assignment for 4.5. Why is this? Anybody want to spoil the surprise? Everybody want to know the surprise? A couple people know the answer probably. We're trying to find area, right? This one represents area. Ends up there's a link between finding the area and finding an antiderivative. If you can find the antiderivative, you can actually find the area. There is a link between the two. Yes?
Well, because you subtract the antiderivative
Alright,
of...
since you want to be very detailed and very much spoiled for us. The mini lesson for Friday. What did we say was the value of this? In case you memorized the formula, I said don't bother memorizing it.
What? The limit?
Alright. What would be the value of this?
Be 1/2 x squared plus c.
1/2 x squared plus c. How do we know that? How can you check?
You can derive that and get the same thing each other.
Yeah, we use the word derive way too many ways now. How do we check this? Take the derivative of 1/2 x squared. You get what? 1/2 times 2 times x to the minus 1. So x to the first power, which matches my integrand. So because the derivative of this is this would be the antiderivative, right? And if I want all antiderivatives, I just put a plus c here. Does that make sense? Well, what we're gonna say is the integral from a to b, so the definite integral is the same as this formula evaluated from a to b. So that would give you 1/2 b squared minus 1/2 a squared. And this will actually be true in general. The integral from a to b of f of x dx is equal to f of x evaluated from a to b, which is shorthand for saying this, plug in the numbers, subtract, for any antiderivative. Capital F of x. So that says the derivative of capital F of x must be little f of x. If you can find an antiderivative, you can find the time derivative. There's a reason we use the same notation. They're actually solving almost the same problem. Because you can use this answer to solve this answer, or find this answer. But y'all don't know that till Friday, so like, forget it. It's on video. Yes?
So then why did you ask if anyone wanted to spoil the surprise if you didn't want us to spoil the surprise?
I was probably going to. Because otherwise, why in the world did we cover 4-4 when we did? This section makes no sense in context. And we're using the exact notation it looks like we would need to solve something else. Alright? So that is why this all relates. All of chapter 4 is finding area, including this section that looks like it has nothing to do with area. This one is laying the foundation so you can find area in the next section using a different way. Alright? Of course, there is one problem. You want to find antiderivatives? It really assumes you know how to find a derivative. So, some people notice this in their reflections, and it looks like it's a lot of rules, easy to make a mistake. If you're doing one thing forwards, one thing backwards, it's easy to use the wrong rule. Like the power rule looks a little bit different now. I have one kind of advice for how to avoid those issues.
Change them into the power rule.
Higher level than that. Every time you find an antiderivative, immediately check it. And why would you do that? When you go to check it, you're using all the rules from chapter 2. As long as you're keeping those rules in your mind when you check it, you're less likely to make the same mistake twice. So the thing we're good at is checking. Checking is normal power rule, right? We are good at this step. This was chapter 2. Always do this step and make sure it matches what you were given. So like you might be creative going from here to here, but you're not going to be creative going from here to here. This is what we know how to do. This is formulating at this point. And it's true, some people made the comment there doesn't seem to be an obvious pattern to finding antiderivatives. Ends up, that's true. There is no product rule, there is no quotient rule. All these nice rules we have for finding derivatives only work one direction. So a lot of it is a little bit more guess and check, or kind of problem solving or puzzle solving. If you look, you have to kind of really understand your derivative rules, look at it, and make a good guess about what the antiderivative would be, which is hard, right? But you can always check. And usually when you're checking, what if you check and you get the wrong answer? It's not the integrand. By doing that derivative rule, you might see where you missed something. All right? Our goal is to go backwards when you're going forwards and it doesn't work. There's a reason it didn't work that might kind of give you a clue as to what went wrong. Always check. That is the best advice I can give you. All right? If you take Calc B, you have another whole chapter on just integration rules and how to do these in general. And it's because you don't have a thing like a product rule or a quotient rule that you have to always be more creative. So there are some ways we can do it, but it's way less direct than finding derivatives. Derivatives, if you had a product, you know you use the product rule. You had a quotient, you knew you used the quotient rule. Going backwards, that's not always the case. All right, so there are a couple formulas to keep in mind. The main one is the power rule. What does the power rule say? So it says what? I want to find the integral of x to the k. I want to find the antiderivative. I add 1 to the power and divide. Why would this make sense? How do we find the derivative of a power? Move the power down and subtract 1. So essentially you multiply and then subtract. What is the opposite of multiply and then subtract?
Divide and then add.
Which one do you have to undo first if you're going the opposite direction? Multiply, then subtract. Go the other way, you undo the subtraction, and then you undo the multiplication, right? So what do you do first? I'm going to undo subtraction, I have to add. And then after I add, that is when I divide. So that is why it's first add a power, or add 1 to the power, and then divide by the new power. Right? That is undoing the power rule. Yes?
Although, why are there negative signs in front of everything?
Those aren't negative signs. It was a itemized or list, and it didn't want to do bullet points anymore. These are my notes. I was supposed to do these. I also didn't want to write them all down. Alright. So this one, add, then divide. It's easy to mess up that order. It's easy to divide first, something like that. Think about why it's this order. Alright. This one we kind of knew, right? What's the derivative of natural log of absolute value of x? Just one of reference. So like a lot of these, we say they're new formulas, but really erase this and put a ddx over here, and that's the one we memorized in chapter 2. This one looks a little bit different. I actually don't ever memorize these. Like this one, it might be worth memorizing, but e to the kx isn't worth it in my mind. So what is the antiderivative of e to the x? E to the x is its own derivative, and then you have to add plus c. So the derivative of that is e to the x. So then, what happens if you take the derivative of e to the kx?
You multiply by k, and then,
I would get this.
yeah.
Why do I get this? We kind of skip a step when we know the formula. It would be e to the kx times the derivative of k times x. So k e to the kx. So it's a chain rule, right? So now when I say find the integral of e to the kx, because of that k sitting there, I know this probably has something to do with the chain rule. Now, actually there is a good technique for undoing the chain rule. If you've ever seen it, it's called U substitution. We technically don't cover it in this class because it's in the next chapter. If you know it, all you're doing is undoing the chain rule. And if you ever want, I can kind of teach it to you because we're basically going to hint at it and never call it that. Alright? But like, I know this was undoing the chain rule. What happened here when I took the derivative? I had to multiply. So if I'm going the opposite direction, what do I assume? I need to divide. So this is what, 1 over k e to the kx plus c. And what can you always do? If you just make up a formula, that's actually okay in this section. You can make up any formula you want. What do you do after that? Check. So let's say I just pulled that out of a hat. How do I know if it's correct or not? Take the derivative, I get all this times k, so the k's go away, and I just get e to the kx. You can pretty much write down anything, just take the derivative, see if it works or not. But then there are better guesses than others. When I see that k there, I know I either need to multiply or divide. Now if I think about derivatives, and derivatives I had to multiply because of the chain rule, so here it makes sense I'm dividing as the opposite direction. But if you're ever not quite sure, you can always check. Right? If you know you need to either multiply or divide, and you don't know which one, and you're in a panic, write one down, check it. Then if that doesn't work, it's probably the other one. All right? So like all these, you kind of get extra formulas, but a lot of them are you just remember your basic derivatives, and then either multiplying or dividing is with the chain rule or something. All right? Alright, any questions so far? Alright. No more presentation. Very well. I'm gonna do this example. I want the directions say verify the integral of cotangent of x is this formula you would have never ever guessed. I shouldn't say never ever, but why would you guess that? That looks weird, right? And now you think back, did we ever have a derivative formula where the derivative of something is cotangent? We could find the derivative of cotangent, but was cotangent ever on the right side? We had what, cotangent times cosecant or something like that? We never had just a cotangent over there? That's because the antiderivative is not something you would just guess. We never told you what is the derivative of log times log of sine. So then the question, how do we verify that? If it's not something we know.
Verify you can work backwards from the answer you use.
Always work backwards. This is a key thing that people forget. So we're given the formula, the integral of cotangent of x is the natural log of sine of x plus c. When somebody says verify, that means we gave you what the answer is, just make sure this answer works. Don't come up with the answer. You don't have to derive the answer. You don't have to come up with it from scratch. You don't start on this side. Right? That would be way harder to do. So by verify, what does it mean to verify? What has to be true? The derivative. So I'm claiming this is the antiderivative, which means to verify it, all I need to do is find that derivative and see if it's the integrand. See if you get cotangent. I don't start with cotangent and try to come up with a way to get this. That looks, I only halfway believe this formula because I haven't checked it. So I definitely don't want to go this direction. If it looks surprising and you have no idea where it came from, that is the wrong direction to go. All right. This one, I can verify this, right? Yes.
I think I can kind of see right off the bat without.
There's a way to come up with it. So, and I can mention that, I guess. What did I get here? 1 over sine of x times the derivative of sine of x. No sine of x over sine of x, which is the definition of cotangent of x. For something that looked entirely crazy, that was too easy. Verify means you know the answer, or we're telling you what we think the answer is, check the answer. Don't come up with the answer. Alright, where did it come from? I wasn't going to do this. Let's say I want to integrate cotangent of x. I would actually write this as cosine of x times sine of x. Again, don't do this. This is the wrong way to solve the problem. Unless you're in calculus, you can solve this. I know the derivative of cosine is sine. And I know the derivative of sine is cosine. Okay, I ignore the negative sign. But like derivative of one is the other, right? Roughly. What I want to claim is there's a chain rule that showed up in here. So I know the derivative of sine of x is cosine of x. Which I have a cosine of x here. So what's the idea? This is acting like 1 over sine of x times the derivative of sine of x. That's the same thing, right?
And then.
What in the world would give me a sine of x on the
A natural log function.
natural log? So I need something where, for some reason, I divide by sine of x and then multiply by its derivative. What does that look like? That looks like when we did the derivative of u of x was 1 over u of x times u prime of x. We had that formula, or that's the chain rule, right? So when I see this template, it looks like it came from here. So that's where this comes from. This is the natural log of sine of x. And then because I took an antiderivative, I write plus 2.
So when you say that this is the wrong way to do it, does that mean that's the wrong way to do it for this problem?
For this problem, if the directions say verify, this one is the verify.
But it's
This
still-
one is the derive. So start with here and show it's this. They are two very different problems. And this is about as bad as it would ever get in this course or come up with something
So we might have to do it.
in the homework. I probably wouldn't put it on the test. It's too hard for a test. But the key here is recognizing this formula. That's a formula we know, right? The derivative natural log of something is 1 over, and then the chain rule says multiply by the inside part. So anytime I see 1 over something times its own derivative, I know that came from a natural log. So I can go backwards now. A lot of finding antiderivatives is pattern recognition. All right? It's really, the best thing to do is go back to that chart of derivatives and really look at it. And now it's when you see this type of form on the right-hand side, you know it's linked to what this was on the left-hand side. When I see 1 divided by something times its derivative, I know that's based on natural log. Now I might not know the exact formula, so what do? Make a guess and check it. Or a lot of guess and check. Alright, so we only have one more example I want to do today. We'll do several examples tomorrow. Your homework's going to be due Thursday night. So let's say I wanted to find the antiderivative. We're going to make this look as bad as possible. Of this. Not the one you thought would be my second example. Let's just put this lesson on steroids.
I'm sorry, but we have like a minute left.
Hmm?
We have like a minute left. How are we going to...
So you're trying to break this apart into fractions and different pieces and look at each piece separately?
Well,
Like if we're finding derivatives, you would break this apart into small pieces?
Right. So you
Yes.
look at it, if you look at it like I'm looking at the top, the bottom, minus the top.
The biggest skill, the worst problems, is taking a holistic approach. I have no idea. I know this came from a derivative rule. If it came from a derivative rule, which rule does it look like it came from?
Quotient?
Quotient rule. I have something minus something divided by something squared. That sounds like a quotient rule. So what do I notice? What's the derivative of sine of x? That gives me cosine of x. What's the derivative of x squared plus 1? 2x, which is the other thing I have sitting here. Which one needs to be on the bottom if this is a quotient rule?
Sine x?
Sine of x. So I know I need a sine of x on the bottom. What would be left on the top?
X squared plus 1.
X squared plus 1. Does it check? So the whole idea, holistically, this looks like a quotient rule. So it looks like the result from a quotient rule. So does this check? What's the question rule say? Take your bottom function, multiply by the derivative of the top, subtract the top function, multiply by the derivative of the bottom, all divided by the bottom squared. If this is your top function, this is your bottom function, you get exactly this. The worst looking thing possible suddenly was, you don't even have to check it. Like you can check it in your head. That is how usually the worst ones will work out this way in this section. Right? It's not, we're used to break this apart into small problems. Like you want to say it's the integral of 2x divided by sine of x minus whatever is over here, and like break it apart. The hard thing now is you have to think of is this is my net result after something else. What did it probably come from? And then looking at the whole form of it, I would say probably a quotient rule. Right? It's all about making an educated guess in some ways. Right? Ones we can do like power rules, that's fine. But the ones we can't just do a power rule, now you're looking at your chart and thinking, where could this have come from based on derivative rules? Is it a derivative I recognize like inverse tangent? Is it or log in a triangle? Or is it something like quotient rule? But we don't have like formulas to undo quotient rule. So you always have to really put some thought into it. All right, we'll do lots more of these tomorrow.